Hello and welcome. If you've got a physics exam on the horizon, you're in exactly the right place. We're going to break down motion, everything from speed and velocity all the way to the wild physics of a skydiver. My goal is to make this your strongest topic. So let's just dive right in. So are you feeling a little overwhelmed by all the speeds, velocities, and those kind of squiggly lines on graphs? Yeah, trust me, you are not alone. But don't you worry. By the end of this, you're going to see how all these ideas are actually pretty straightforward once you know the right way to look at them. Okay, here is our game plan for today. We're going to start with the basics, speed versus velocity. Then we'll level up to acceleration. After that, we are going to become absolute masters at reading both distance time and speed time graphs. And for the grand finale, we'll tackle that classic real-world example, free fall. This is your roadmap to absolutely nailing these questions.
Right, first things first, speed versus velocity. Now this is a classic exam question. It's designed to see if you're really paying attention to the small details. And while the difference seems subtle, it is absolutely crucial.
So what is that big difference? Well, it all just boils down to one word, direction. Think about these two cars, right? They're both moving at a speed of 20 meters per second. But because they're headed in opposite directions, their velocities are totally different. Speed is what we call a scalar quantity. It's just a number. But velocity? That's a vector. It's got both the number and the direction. Getting that difference is a guaranteed point on your exam, so lock it in.
Now for your first big exam hack. We all know the formula, right? Speed equals distance divided by time. But what happens when the question asks you to find the distance or the time? Instead of trying to memorize 3 different versions of the formula, just use this brilliant little tool, the formula triangle.
It is honestly this simple. Let's say you want to find distance. You just cover it with your finger. What's left? Speed and time, side by side. So you multiply them. What if you need to find time? Cover it up. Now you see distance over speed. So you divide. This little trick is an absolute lifesaver when you're under pressure in an exam.
Excellent. So now that we've got speed and velocity figured out, let's talk about what happens when they change. And that brings us to our next key concept, acceleration.
So in the simplest terms, acceleration is just any change in velocity. If you're speeding up, that's positive acceleration. If you're slowing down, that's negative acceleration, which, we usually just call deceleration. It's all about how quickly your velocity is changing.
And this visualizes it perfectly. A rocket taking off into space, that is some serious positive acceleration. Its velocity is just increasing like crazy. And a car hitting the brakes for a stop sign, that's deaccelerating. Its velocity is decreasing. It's simple, it's visual, and it's really easy to remember.
And hey, guess what? There's a formula triangle for acceleration too. This is another essential for your exam toolkit. You've got change in velocity at the top and acceleration and time at the bottom. The exact same rules apply here. Just cover up what you need to find, and the triangle tells you exactly what to do.
Okay, let's switch gears and talk about graphs. Now, I know they can look a little intimidating, but I want you to start thinking of them as a story. A distance-time graph is literally just telling the story of an object's journey, showing you exactly where it is at any moment in time.
The secret to reading these graphs is actually really simple. You just look at the steepness of the line. We call that the slope, or the gradient. And that gradient tells you the speed. So a steeper line means you're going faster. A more shallow line means you're going slower. And what about a completely flat horizontal line? Well, that means you've stopped. Your distance isn't changing at all. If you remember only one thing about these graphs, please make it this. Write it down, highlight it, whatever you need to do. On a distance-time graph, the gradient of the line is the speed. If you can calculate that gradient, that's the rise over the run, you have found the speed. This is a classic exam question every single time.
So what about curves? Well, a straight line means your speed is constant, but a curve means your speed is changing. Look at the green line. See how it's getting steeper and steeper? That means the speed is increasing. It's accelerating. Now look at the red line. It starts off steep and then gets flatter and flatter. That means the speed is decreasing. It's decelerating. Let's see how this all comes together to tell a story. In section A, Osei is just walking at a steady speed. See? The line is straight. In section B, the line is totally flat. He's not moving at all. He's probably sitting on a bench reading a book. But in section C, whoa, the line is much steeper than it was in A. He's running home now, covering a lot more distance in the same amount of time. See? It's just a story. Okay,
So you've pretty much mastered distance time graphs. Are you ready to level up? Let's get into speed time graphs. These are even more powerful because they tell us not just about speed, but also about acceleration and the total distance traveled.
For these graphs, there are 3 golden rules you absolutely have to know. First, the gradient isn't speed anymore. On this graph, the gradient is the acceleration. Second, a flat line doesn't mean you've stopped. It means your speed is constant, which means your acceleration is 0. And third, and this is the really clever part, the total area underneath the graph gives you the total distance the object has traveled.
Let's put that last rule into practice with a typical exam question. This graph shows a car's entire journey. It accelerates, drives at a steady speed, accelerates again, and then slows down to a stop. So how do we find the total distance it covered? Well, we have to find the area under that entire shape.
Now, I know that looks like a really complicated shape, but here is the exam tip. Don't panic. You just break it down into simple shapes that you already know how to deal with, like the triangles and rectangles you see here. The method is always to calculate the area of each of those little shapes one by one.
And then you just add them all together at the end. For this particular journey, the total distance traveled is 2,175 meters. Yeah, the calculation might take you a minute, but the method is always the same. Break it down and add it up. Okay, for our final section, we are tackling the big one, free fall. Think of this as the final boss of motion because it brings everything we've learned together: acceleration from gravity, changing forces, and graphs that tell the entire story. When a skydiver first jumps out of a plane, the main force acting on them is their weight, pulling them down, so they accelerate. But as they get faster and faster, the upward force of air resistance gets stronger and stronger. Eventually, you get to a point where that upward push from air resistance perfectly balances the downward pull of their weight. The forces are balanced, so the skydiver stops accelerating and falls at a constant speed. We call that terminal velocity. And this speed time graph tells that entire story perfectly. Look, at the beginning, you have this steep gradient. That's the rapid acceleration. Then, the curve starts to flatten out as they reach that terminal velocity. Then, bam, the parachute opens, air resistance suddenly skyrockets, and you see that rapid deceleration. Finally, they settle at a new, much slower, and much safer terminal velocity to land. All of that physics captured in one single curve.
So, there you have it. We've gone from the simple difference between speed and velocity all the way to the complex journey of a skydiver. You now have the tools and the tricks to analyze motion and really ace those exam questions. So the only question left is, now that you can see the physics behind every single movement, what's the first real-world thing you'd want to graph? A car pulling away from the traffic lights? A ball being thrown in the air? The physics is all around you. Good luck!